First, I'm gonna give you an overview about the autoencoders, and then we'll go through the provided code for this assignment. About the autoencoder, I know you're already familiar with the concept, but just a quick review. So assume that this is a network, gets, for example, an input like an image, and then classify it to two clusters. For example, this one is cat, and this one is dog. So we feed the image into the network from here, and this is our hidden layer, and then the model predict two values for this, from 0 to 1 for each of categories, and then and the sum of them should be 1. And then we decide, for example, it says 90% cat and 10% dog. So we say, for example, this is a cat. So this is a classification concept. Now assume that we have another network which has similar architecture, but they in reverse order. So after retraining this network, so this network takes an image in the input and generate an image in the output. So we call the first network encoder and the second one decoder. And so this second part of the network can generate the original image from the latent variable in the middle of the network. And these are the same nodes. So in this way, we can, for example, 28 by 28 image, we can generate a latent variable or a representation of 2 dimensions of that image, and then reconstruct it again. And maybe if we train a good network, we can generate new samples. For example, if this network, consider we train this network on face image. So we feed a face at the beginning of the network, and we reproduce it, and then we calculate the loss during the training process. We'll talk about it. And then after training the network, we can get a new sample, for example, a new values for this latent variable, and feed that through the decoder to generate new faces. So we call this kind of network as generative models. Those are able to generate new samples or unseen samples. And as you may know, this representation is important for compression, visualization, and also learning a representation to generate new samples. Okay, this is about the concept of autoencoder, and then about the PyTorch, how we implement a network in PyTorch. I should have, okay, here. Okay, this is, can you see the Explorer, this page?
Yeah.
Okay, perfect. Okay, this is a sample from the PyTorch, and the best source to learn about PyTorch is their website. It is well documented and has many tutorials. But the main concept is we define an architecture of our network. For example, this architecture, or for simplicity, let's talk about this again. Okay, for the assume that we already defined the architecture of our network. So we have, for example, four dimensions here, 1, 2, 3, 4, again 4 dimensions here, and 2 dimensions here. So our architecture has linear layer of input size 4 to output size. I'm writing pseudocode, which is more similar to PyTorch framework. And the output dimension is 4 again. So this linear layer represents this. And then for this part, again, another linear layer. Input is again 4 and output is 2. And so we feed a sample of 4 dimensions to the first linear layer and then to the second linear layer and compare with the output. For example, we have labeled data for this cat and dog classification task. So we should compare the output for a sample and then calculate the mean square error loss. So in PyTorch, we have data, we have architecture, and training. Okay, we have talked about the architecture, now about the training. First, we need to load the data. Data is, in PyTorch, there is a library named data loader, which is not used in this example from the PyTorch website. You can find something that use the data loader, but I will go through the provided code and the data loader part. And then after loading the data, this is the, for example, the definition of architecture of the network in PyTorch example. So first of all, it should be a child of NN module. NN is neural network from Torch. Torch NN as NN. And then 2 functions should be defined. The first is the constructor. For example, here, this is a convolutional neural network, and self.conv1 is a convolutional 2D network, 2-dimensional, and its parameters. So for example, you can click on this conv2D and see the definition of everything, and even source. And then another layer and so forth, and also a forward function. So for defining architecture or your model class in PyTorch, you need to implement these 2 functions, and the forward function passes the sample X through the network. So for example, here we were talking about 2 linear layers. So in our forward function, self and X, for example, this is our sample. It should go, for example, output 1 equals to self dot, for example, linear 1 X, and then O2 equals to self, so forth. And the input should be O1. So first it goes through the first layer, and then we feed the output of first layer to the second layer, and so forth. How many layers you have, you can define any kind of architectures, but the point is you need to define layers and then forward function. Okay, so this is about the architecture or model class, and then we want to train this network. To train this network, we need to load data and then feed the data to the model using this forward function. Let's see what we have. This is parameter initialization. It's not important. Okay, here we don't have a data loader in this example, but it is defining the input like this, and then okay, this is the network, an instance of the implemented class, and then input goes to the network. It implicitly calls the forward function when you write the instance name and input, and gets output. So this function goes to this process. First, x equals to f max, and x equals to f max full 2D, and so forth. And finally, it returns x. So this is the output. And then we have target or labels. And defines a mean square error loss, calculate loss. So this is how we calculate loss. Input goes to the output, goes to the network and generates output. We have target. We define the loss function and calculate output and target loss. So here we calculate a loss. Now we need to do the back propagation to backpropagate this loss error and train the network. To do that, we need to define an optimizer. Oh, by the way, before calculating loss, I guess you need to do the zero grad thing. It is already, oh no, we calculated loss, then we do the network.zero grad. It removes gradient from the previous step. You know, we train our network through many epochs. So it removes the gradient and then loss backward. This is backpropagation and trains the network. Loss backward, it calculates, I guess, the loss for all parameters in the network. And now we need to step our optimizer. Defined optimizer steps. This is not well organized in this example, but in our code, it is, I guess, better. Okay, so once again, let's summarize everything here. Okay, model, define the architecture, has a constructor and a forward function. Then this is for the model, and then for the training, we feed sample input goes to the model. Loss calculation, loss backward, optimizer step, and zero grad, and we do the same for each epoch. So there should be another for loop over this. You will see that we also have another for loop here for data. Because, for example, assume that we have, I don't know, for example, 1,000 samples in our data set. So we have 1,000 samples, and we pick batches from that. So each batch has, for example, 128 samples, 128 samples. On two extreme situation, you might input the entire data set, 1,000 samples here as input and calculate the loss. And also you might input one by one and calculate loss. So this is more about stochastic gradient descent. So we'll have one for loop for epochs and one for our batch. dataset, batchified dataset, and then model input, loss, and so forth. Okay, let's jump to the code. Okay, this is provided Jupyter Notebook. First, here we have inputs, and then this is the model architecture. You can see that we already implemented everything. You need to define the architecture of the encoder and the forward function for it, and the architecture of the decoder and forward function for it. And then you also, because these are two inner classes in our autoencoder class here, we also need to implement the forward function for the autoencoder. So there should be another forward function that feeds the input to the encoder, and the output goes to the decoder for the reconstruction process and returns the X. And here we, since we train an autoencoder in unsupervised fashion, it means that we don't have the label. We just want to compress the data and reconstruct it from the compressed latent variable. So X would be our target. And for training, we have learning, number of epochs. You need to maybe modify these things. For example, increase the number of epochs and see what happens. So we define an instance of the autoencoder with the latent representation dimension. For example, 2, you can see that this latent representation goes to, this here goes to the as output size of encoder and input size of decoder. Here, output size and input size. So this is our latent representation. And as I told you, the encoder and decoder usually have the reversed architecture, but in this assignment, you need to change a few bit of decoder part. Okay, and this is the training process. We define an instance of the autoencoder, the trainer. The trainer is already implemented in the starter.py file, and then we have a for loop over number of epochs and train, turn validate, and so forth. Now let's go to this autoencoder starter.py. This is the scatter plot. I will go through it later. Plot kernel, that's an important. Display image, it's not important. Okay, autoencoder trainer. These are initialization things, and then transforms the image to be appropriate for the training process. It's not important, but yes, here is the loss function. So you already have the mean square error loss function, and it gets reconstructed X and actual X, or the original input, and compares the reconstructed with the original input for the training process. So it gives our loss, and then somewhere we should have the gradient things. Loss function backward. Yeah, here. Loss backward, and then optimizer that step. So you don't need to worry about this, but I just want to know what's going on here. And yeah. Now, so we train the network, and then this torch that no grad means we when we feed the input to the model, here we define the model, we get the model from the trainer, And then, yeah, we want to get the latent variable. So we only use the encoder part of the network, and this is the input that goes to the network. And the point is, since we don't want to train the network at this stage, so we set it to torch.nograd settings. So because we don't need the back propagation and loss function and everything. And then here we get the latent variable of the model, and then generate image by sampling from bottleneck features. So we randomly generate few numbers in the bottleneck. And here we try the reconstruction quality. So we get a few images from the data set, and then we, again, with torch-no-grad, we reconstruct the image. So we feed the image to the model instead of the encoder. Here we needed to we wanted to visualize and see the latent variable, so we just used the encoder. Here we wanted to generate new samples or unseen samples. We just use the decoder, and now we want to see the reconstruction quality, so we use the entire model. Encoder, compressed or latent variable representation, decoder, original input image, or reconstruction of the original image. So I guess I told whatever I wanted. Oh, one more thing. At some point, you need to use this scatter plot function. So for 2D dimension, it is already implemented here. So when you call this function, it plots a 2D latent representation, 2D image of your latent representation, and it should be something like this. For a higher dimensionality, here you need to use t-SNE, and the t-SNE is a library. You can just import it. I guess we already did that. No, you need to import it, and then say whatever dimensionality you need to map it. So at some point, your latent representations will have, for example, 30 dimensions, and you feed that 30 dimension to the t-SNE library, and it provides 2D dimensionality of the latent representation, and then do the same for visualize the output.